Guys, this is dark and it has huge mass and it's small. That's 3 smoking guns right there implicating a supermassive black hole. Space can be scary to think about, the dangers that lurk within the vast expanse of space can be terrifying. While this applies to the entire concept of space exploration, the one part of it all that has always been intriguing and terrifying at the same time has been black holes. These beasts of power have been the subject of countless researches all across the globe. Scientists have been trying to figure out just what black holes really are and what lies in them, but all of that changes now. Neil deGrasse Tyson just revealed something huge, and our black hole is less massive than the one in the center of the Andromeda Galaxy, our nearest big galaxy. So, we have black hole envy. I think we do. We finally see what's inside a black hole, and well, all of it might just blow your mind. So join us as we take you on this intergalactic journey and answer one of history's most asked questions ever: what is a black hole? A black hole is an extraordinary phenomenon found in space that is created from a massive explosion. The black hole's mass is concentrated in an incredibly small region, creating a gravitational force so intense that nothing, not even light, can escape from it. Once something is in there, it's going to stay in there forever. These forces of energy come in various sizes, ranging from stellar black holes, which can be a few times the mass of the Sun, to supermassive ones that exist at the centers of galaxies and can have millions or even billions of times the mass of our Sun. Scientists have observed the effects of black holes indirectly for decades now, and with every piece of data, we uncover hundreds of secrets. Even though it seems like they're so massive and powerful that they can't possibly have an origin story, they do. Black holes don't just exist in space, they're created. They need the remnants of massive stars that have exhausted their nuclear fuel to be born. These stars undergo a supernova explosion, a spectacular event that marks the end of their lives. During a supernova, the outer layers of the star are violently expelled into space while the core undergoes a gravitational collapse. But not all collapses are going to be the same here. If the core's mass is several times larger than that of our Sun, the force of gravity overwhelms all other forces, causing the core to collapse inward. This collapse is so intense that it compresses the mass into an incredibly small volume, creating an object with a gravitational field so powerful that nothing will be able to escape its grasp, thus creating a black hole. The size of a black hole is determined by its mass. Stellar black holes, which are the most commonly known type, have a mass range from a few times to several tens of times that of our Sun. At the core of a black hole lies the singularity, a region of infinite density and space-time curvature. According to our current understanding of physics, the laws of nature break down at this point, and our conventional theories cannot fully explain what happens within the singularity. To truly understand the nature of singularities, we would need to think outside the box a little. In the world of physics, a singularity refers to a point in space-time where certain quantities become infinite or undefined. These singularities appear in various theoretical contexts, such as at the beginning of an expanding universe, which is commonly known as the Big Bang singularity, and within the inside of black holes. When we study the Big Bang singularity, a fundamental challenge comes forward. According to the theory, the universe originated from an extremely hot and dense state about 13.8 billion years ago. But as we rewind time toward this initial state, the equations of general relativity, which govern the behavior of gravity, break down. This breakdown implies that our current understanding of physics cannot fully describe the conditions at the moment of the Big Bang. Resolving this issue requires a theory that combines general relativity with the principles of quantum mechanics. You see, black holes contain singularities at their cores. These are regions where the gravitational pull becomes infinitely strong and spacetime is highly curved. According to general relativity, matter and energy that fall into a black hole reach its singularity and become infinitely compressed. This concept, too, is beyond our concepts of physics. Adding to the problem here, the challenge of singularities has motivated scientists to search for a theory of quantum gravity, which aims to unify the principles of general relativity and quantum mechanics once and for all. So there's at least a little bit of clarity here. Quantum gravity seeks to provide a framework that accounts for the behavior of spacetime on both cosmic and subatomic scales. A theory like this could potentially offer insights into the nature of singularities and how the universe really works. One approach to addressing the issue of singularities is the theory of loop quantum gravity. This theory suggests that at extremely small scales, spacetime is quantized, meaning it consists of discrete indivisible units everywhere. These fundamental units are often referred to as loops or spin networks. In loop quantum gravity, the concept of quantization is applied to spacetime itself. This means that spacetime isn't considered a continuous and infinitely divisible entity, but rather a collection of discrete elements. These discrete units of spacetime are often seen as interconnected loops or networks that represent the underlying structure of the fabric of the universe. Within the framework of loop quantum gravity, singularities associated with black holes and the Big Bang could be resolved. One of the key insights of this theory is that at extremely small scales, the discrete nature of spacetime prevents the occurrence of infinite densities and curvatures that give rise to singularities in classical general relativity. For example, in the context of black holes, loop quantum gravity suggests that as matter collapses toward the core, the spacetime fabric becomes increasingly tiny. The size prevents the matter from reaching an infinitely dense singularity. Instead, the collapsing matter encounters a quantum bounce near the core, where it rebounds and begins to expand again. This scenario leads to the formation of a new spacetime region inside the black hole, often referred to as a quantum black hole or a bounce region. The bounce region replaces the classical singularity, allowing for a resolution of the singularity problem. Similarly, in the case of the Big Bang singularity, loop quantum gravity proposes that the universe's initial state was not characterized by an infinitely dense and singular point. Instead, the universe emerged from a pre-existing quantum gravitational phase where the nature of spacetime prevents the occurrence of a singularity. This provides a new perspective on the origin and evolution of the universe, avoiding the singularities present in classical models. The search for a unifying theory is driven by the desire to reconcile the classical treatment of singularities in physics with the principles of quantum physics. Bridging this gap could potentially yield new insights and resolutions to the challenges posed by singularities. But then again, there are so many types of black holes that even this proposed solution gets left behind. Stellar black holes are the most commonly observed type of black hole in the universe. As we've briefly touched upon earlier, they are formed through gravitational collapse at the end of a massive star's life. The way all of this works is that once a massive star has consumed all its nuclear fuel, the outward pressure generated by nuclear reactions can no longer counteract the force of gravity pulling inward. The gravitational force becomes dominant, causing the star to collapse under its own weight. This collapse results in the formation of a stellar black hole. But as the star collapses, it becomes incredibly compact, packing a significant amount of mass into a very small volume. As a result, stellar black holes typically have a mass ranging from a few times to about 20 times that of the Sun. Although despite their mass, they have remarkably small sizes, their diameter is only a few kilometers, which just goes to show how extremely dense they are. The immense density of a stellar black hole leads to the formation of an event horizon, a boundary beyond which nothing, not even light, can escape. This event horizon marks the point of no return, where the gravitational pull of the black hole becomes so strong that any object or information that crosses it is trapped forever within the black hole. Then we've got intermediate mass black holes. While the precise mass range for intermediate mass black holes is still something scientists need to put through more research and refinement, they are generally thought to have masses ranging from thousands to tens of thousands of times that of the Sun. So that would be much denser than a stellar black hole. The formation mechanisms of intermediate mass black holes are still not entirely understood, but there are two primary scenarios that are currently being investigated. The first possibility is that they form through the merging of multiple stellar mass black holes in regions of space with a high concentration of massive stars, such as globular clusters or galactic nuclei. Interactions between stars can lead to the formation of binary systems. Over time, these binary systems can merge because of gravitational interactions, eventually resulting in the creation of an intermediate mass black hole. The second formation scenario proposes that intermediate mass black holes form through the direct collapse of massive gas clouds in the early universe. These gas clouds, which are dense regions of primordial matter, can undergo rapid gravitational collapse, leading to the formation of an intermediate mass black hole instead of a star. This process may have been more common in the early stages of galaxy formation when gas concentrations were higher, which is why stellar black holes are a lot more common now. One of the main things about intermediate mass black holes is that they're extremely challenging to detect because of their mysterious nature and the limited number. However, their presence has been detected through indirect means, such as studying the dynamics of stars and gas near these potential black holes. Not only that, but recent observations have provided some evidence for the existence of intermediate mass black holes in galactic nuclei too, so they might not be as rare as we think they are. Then we've got supermassive black holes. When scientists first observed them, they were stunned. We usually tend to think of something enormous as a large structure. For example, we wouldn't call the Grand Canyon a large ditch, right? So the idea of supermassive black holes always made people think of extremely dense objects that could never be bigger than the average house. But when scientists saw supermassive black holes, they were stunned at the possibility. They're some of the most massive and powerful objects in the universe.